Okay. Thank you very much for the introduction. And it is a great pleasure to be here to present my work joint with Wang and also Sebastian Galliani at Maryland. So this paper, we focuses on the premises and the limits of the RCTs. So nowadays, we all know that the randomized controlled trials has become the golden standard for evidence-based policy evaluations, because it provides very clear identification of the treatment effects. But today, I want to draw your attention to the two limitations that we want to emphasize and many RCTs share, which are the short-run duration issues and also the indulgence recruitment issues. So the short-run duration issue of the RCTs is a fact that many policies implemented and evaluated by RCTs, they usually take much shorter duration than the actual policy we want to implement. And the second issue is the indulgence recruitment issue, refers to the case when the RCT, when they implement the policy interventions, they many times recruit research objects subject to certain eligibility criterion depending on some indulgence outcomes. And we think that necessarily introduces some selections in the population of research. So in this paper, when we demonstrate that there is a problem, which is if we want to evaluate of some impacts of some policies on the agents who are forward-looking, and there is a certain type of heterogeneity among them, unobserved heterogeneity, then we claim the RCTs with these two features, the short run and the indulgence recruitment, may not be able to identify the average treatment effects of the actual policy we really want to know. So, later I'm going to formalize these two limitations and the problems in detail with math. But before that, let me give you an overview of our solution to this. So we propose to combine a structural model with multi-arm RCTs to recover the actual policy ATEs. So we have this three-arm, this is just a demonstration of the multi-arm RCTs in the case of conditional cash transfer programs. So we have three arms. We have the control group, unconditional cash transfer groups, and also conditional cash transfer group. So we are going to use this data, the three boxes on the top, and we are going to relate it to a structural model and theta. And we are going to leverage the dual rule of RCTs. We are going to use part of the RCTs, the two arms from control group and the unconditional cash transfer groups for identification. We leverage this experimental variation to identify the model, and we reserve one arm of the multi-arm RCT data for out of sample validation. In this way, we increase our confidence in the structural models. Okay, and then we use these structural models to explicitly address the two limitations that I mentioned about the short run issue and also the indulgence recruitment issue, right? So we explicitly address the short run duration issue by simulating the full duration policy instead of the short-term policy, RCT policy implementation, okay? And then we address the indulgence recruitment issue by simulating the full population instead of the selected eligible population for the evaluation, okay? So in the existing literature, there has been papers combining structural models with the RCTs, starting from Todd and Walking. They used this control group data for estimation and leave the treatment group for validation. And the paper by Ignacio Maguire and Santiago, they used both arms for identification, leveraging these experimental evaluations for model identification. And one previous paper by Juan, Galliani, and Murphy, they used this dual rule of RCTs, and our paper is going to be in line with those. And there are very good survey papers by Todd and Walking and Juan and Galliani. Okay. In the literature of studying the conditional cash transfers programs and focusing on the schooling outcomes using structural models, the previous papers, they mostly study this Mexico's Progressa case, while we study this relatively newly implemented RCT in Malawi, an African country. Okay. So our main contribution is that we leverage this dual rule of RCT for to have a more reliable structural models and use this structural model to recover the policy ATE with corrections of the two issues. Okay, we propose a methodology for general use, and then we exemplify it with a particular case in the following questions this program. Yes, we have questions? Oh, sorry. Now let me give more details about these two limitations. Okay, so first is the short run duration issue with RCTs. So this is a case when the RCT implemented policy has a shorter duration than the actual policy we want to implement. Using the Malawi cash transfer program as an example. So these cash transfer programs, they target on the girls aging from 13 to 22 in the Malawi country, and they give monies to the households, try to encourage girls to stay in school. Okay. And so they affect girls with this age range. And the ideal goal is to support the girls until high school graduation. Okay. So ideally, we want to implement a policy TPO with TPO length, maybe 6 years, 7 years, longer enough to support them until high school graduation. But due to the budget constraint of the RCT program, the policy actually implemented only for 2 years, the capital RCT. So the capital TPO is much longer than the capital TRCT. And we argue that if the agents, they are forward-looking and they know exactly what's going to be the length of duration for the policy intervention, then when they respond to this policy intervention, it's the behavior, the outcome Y4 is going to be different from the outcome of YRCT, depending on the duration of policy interventions. Okay. So that's the first issue. And the second issue is the endogenous recruitment issue, which happens when there's going to be endogenous selection due to the eligibility recruitment requirement. Okay. So again, using the Malawi as an example. So when the Malawi cash transfer programs was implemented, they recruited girls among all the possible ages in the population, but they require the girls to be unmarried and still in school at the recruitment year 2007. Okay. So this is going to be troublesome if you think about there's going to be unobserved heterogeneity among these households with girls. They have different levels of preferences for schooling. Okay, so then the distribution of this over this unobserved heterogeneity at each age is going to be different for those eligible girls who are still in school comparing to the full population unconditionally. Okay, so here is just one hypothetical illustration of the selection of population over ages. Okay, this is just a hypothetical. But think about, we have 3 types of girls with high and middle and low levels for preferences for schooling. And this blue bar demonstrating this high preference types of households, the fraction is going to be increasing over time. Because having a high preference for schooling, you are more likely to stay in school when the policy experiment starts. So you will be more likely to be available. But that's going to be distribution that we do not want to evaluate. Okay. So here I demonstrated these 2 limitations of RCTs used in Malawi cash transfers program, but it is not very difficult to imagine that these 2 issues exist among many RCT settings. Okay. But I want to convince you that these 2 limitations matter a lot by formalizing this gap between the 2 ATEs we want to that we look at. Okay. So the first one is the so-called experimental treatment effect, ATE RCT, at a particular age A. So which is what we can recover from the RCT data using the very standard analysis. Okay. This is going to be the integral of the difference between the outcomes with policy intervention versus no intervention integrated over the population distribution for the eligible individuals recruited into the program. And but what we really want is to have this ATE policy. This policy is going to be longer enough duration, and it's supposed to be universal for the population. So it's going to be an integral of this green y-pole minus y0 integrated over this distribution mu without this eligibility selection. So these two ATEs are different because this y RCT is different from y-pole due to short round duration issue. And this mu eligible is different from mu A due to this endogenous recruitment issue. We can get AT RCT, but we really want this AT pole. And we need to leverage a structural model to help us map between them. So what we do is just a repetition of our solution in the overview is we have a structural model. This structural model must be good enough that it matches the targeted moments well when we're using this control group and UCT group. And it also matches the untargeted moments very well. That's
So actually, you should address using the reference data.
yes.
But I think the real issue is about the inductance adjustment of the behavior. So then I don't think we have two sources of bias. In the end, there's only one.
There is only one due to the endogenous.
Yeah, to the forward-looking behavior. For the distribution issue, you can actually just weight the first parameter to look at the population, right?
Well, the problem is the distribution is over the unobserved.
If you think about, so when you motivate it, you say about the age and their, so, okay, I see your point. So you think their preference for a school that is not observed.
Yes. Give a question. So we are going to get a reliable enough structural models, and we address the two issues explicitly by simulating full population under actual long enough policy to recover the ATE policy of interest. And so that's an overview of what we're doing in this paper. Now let me exemplify it using a concrete example using this Malawi cash transfers program. I briefly mentioned about some aspects previously, but now let me give you the full information. So this cash transfers program was implemented in Zomba in Malawi, and they recruit never married and in-school girls aging from 13 to 22. They randomly divide them into control group, conditional cash transfer per group, and unconditional cash transfers groups. Okay, and this policy intervention lasted for 2 years in 2008 and 2009, and the recruitment happened in 2007. They randomized this cash transfer amounts for the treatment groups. And the goal of this cash transfer program is to incentivize school attendance and delay the early marriage and early pregnancy. So you can see this is a perfect example demonstrating the two issues that we worry about. And this RCT ATE has been studied by the Bard McIntosh authors 2011 QJE paper. And what we want to do here is to have a structural model that can match their RCT ATE results and address these two concerns of the RCT aspects and then recover the full policy ATEs. So we use this standard dynamic discrete choice model. We model households with girls aged between 13 to 24. For each household in each year for a particular age A, if the girls is unmarried, then they can choose among these 5 alternatives for the choice combinations. Marriage is an observing state. So if you get married, you cannot attend school. But if you are unmarried, then each year you can choose whether to go to school or not, whether to have a sex partner to receive additional income or not. Okay, so these are separate choices, flexibly to be chosen. There are several aspects of the model. So the agents, they are forward-looking. Each household, they are maximizing their expected summation of flow utilities from age 13 to 24. And there is a terminal value at age 25. We allow for unobserved H90. There are 3 types with different levels of schooling preferences. And in particular, if we look at this functional form, so the flow utility we have several parts of preferences, but for schooling here, we have this K types. So alpha 1 can take 3 values from low, middle to high. And we model endogenous fertility, the pregnancy probability, the transition will depend on your certain choices about going to school or getting married and having sex partner and so on. Yes.
Functional forms, it seems to me that liquidity constraints don't play any role in this decision making, do they?
Oh, so what constraint? Liquidity. Yeah. So yes. So yeah, they do not. Well, so that's why they consume everything that's available. That's why they consume everything that's available.
But that's a dynamic.
Yes.
About marriage,
yes.
Thinking about your liquidity now and that will play different.
Liquidity. Are you thinking about savings? Yeah. So as you are saying, this is of course the country. So we assume they consume everything they have every year. So they do not say the consumption. We have this cash transfers entering here. And when they are making decisions, for example, about sex partner, it changes their income. So that's estimated from data. It's exogenous.
There is a dynamic trade. If I get married today, and I may increase my income consumption, but it will generate losses to my income.
The dynamics is considered by this value function. So it's a dynamic problem. Yes. But thanks for clarification. So yes, so the budget constraint is just that the consumption equals to the total family income plus the cash transfers if you are treated. Okay, so here are the value functions and the Bellman equations that characterize how households are making optimal choices among the 5 alternative choice combinations. So the first bullet point, before intervention or during intervention, but for the control group who are not impacted by the cash transfer policies, this value function for a particular alternative D is just your low utility depending on your consumption today, your schooling choice, your marriage choice, having sex partner choice, and your characteristics, including the cumulative the years of schooling and are you ever married, are you ever pregnant, and so on in the omega, plus the discounted expectation of continuation value. Okay. And the optimal choice is just maximizing over the 5 alternatives. That's the bullet 1. So the bullet 2 is the value function during intervention, particularly for the UCT and CCT group. So with a randomized assignment, given your type chi, with Z equals to UCT or CCT, and with a randomized cash transfer amount tau, the households are re-optimizing. So this chi enters this value function. Oh, sorry, I didn't mention that epsilons are the preference shocks related with your alternatives. Yeah. So, so these are the value functions during the re-optimization of the policy with the policy interventions. And here is how we explicitly model that a forward-looking agent, they know when how long the policy intervention is going to last. Okay. So, so the value function in 2009, it's using the value function in 2010, which is basically the same in the baseline case because the cash transfer ends in 2010. So it reverts back to the baseline case with no cash transfer. They know it ended. And going back to 2008, they are using this 2009 conditional value function, which has already incorporated this knowledge of ending cash transfers. So the forward-looking agents, they respond when they are choosing the choices in 2008 and 2009, they correspond to the knowledge that this cash transfer is only going to last for 2 years. The what?
It's the duration of the transfer amount beforehand.
Yes.
So they know for sure it's spent.
Yeah. They know when they are recruited, they know everything about the program.
How large will it look like?
How much work?
What for example?
It's so it varies from I think $4 to I think 40-ish US monthly. But that's a big amount to the relative income in Malawi. So here is more explicitly how this cash transfers enter the budget constraint that changes consumption. So we have this UCT group and the CCT group, but for the UCT group, you receive this unconditionally. But for the CCT group, you can only receive it if you choose schooling to be one. So for the UCT group, there is a pure income effect. While for the CCT group, it's both income effect and also price effect because it offers the alternative cost of attending school. So we brought our model to the RCT data using simulated method of moments. We targeted on a list of the key outcomes, the schooling attendance, the average mark rates, the average pregnancy rates. We also tried to match this age-specific schooling ratios at recruitment, which implies information about dynamic selection. This is crucial to be matched. And we also exert several auxiliary regressions to help identify the model, which are basically a bunch of linear probability models regressing the outcomes on a bunch of covariates. We let the model simulate the data to match those. Yes.
Target points. Why are you targeting the UCT rather than CCT? It seems more natural to target the control and CCT and use UCT to do validation.
So our logic is that UCT has only one effect, CCT has two effects. So it's purely
exactly it provides more information for you.
So it's kind of like we want to stress test our model. Even without targeting this effect, our model can still match it. That's why we are more convinced.
But the elasticity of price, it seems to be identified from the CCT as more transparent.
Yeah, I mean, we can do reversely. But the current situation is even without targeting this, the model matches the CCT outcomes relatively well. But yeah, but this is maybe something we need to think more about it. Thanks a lot. So here are our main fitting results. So these are absolute values of each outcomes, 3 types of key outcomes. And I'm showing you here the control group and UCT group. For the data and model, you can see it's all matched relatively well. These are the targeted moments. And in particular, we capture the pattern that for UCT group with this income effect, there is almost no effect on schooling, which is aligned with this QJB findings, but it reduces marriage and pregnancies. And we also matches this age-specific schooling. So this is the fraction of girls who choose to go to school at different ages for the control group. And I'm showing you the blue line of the data with the 95% confidence interval, and the orange line is the model prediction. So it's within this confidence interval. We match this dynamic selection outcomes. And we examine the model by comparing the results for the CCT group that are not targeted in the estimation. We see that they are relatively well matched, even though we did not target them. The key aspect is that there is significant effect on schooling for the CCT groups. We have to be upfront that there is one puzzle in our result, not just in our model, but also in the QJB paper. Generally, for this Malawi cash transfers program, that they found there is a much higher average pregnancy ratio for the CCT group, which is outside the scope of a standard economic mechanism. So we do not try to reconcile this, but I think it's okay. We are not very worried because we do a good job for explaining the schooling changes for the CCT group. So those are the absolute values. If we take the difference, contrast the CCT, UCT groups to the control groups, we see the treatment effects. I'm showing you this dot with the bars. are the data with 95% confidence interval, and the crosses are the model for 3 key outcomes in different years. You can see that for both UCT and the CCT, it's within these ranges, except this puzzling pregnancy treatment effect, which is fun. So these are the treatment effects integrated over age. But what's even better with the model prediction is that the model matches the age-specific treatment effects for the CCT group in terms of schooling outcomes without targeting it. So this blue line is the data. The RCT recovered CCT treatment effects with 95% confidence interval. It has much larger standard errors because we have very small samples when we divide by ages. I think I only started 25 minutes. Oh, okay. Can I have maybe like 3 minutes? Okay. Yeah. So, but this really gives us a confidence that our model is going to be able to explain what's really happening in the real world. So, now with this powerful, reliable structural model estimated using the RCT data, we want to first assess the dynamic selection issues in the recruitment. We all know it exists qualitatively, but we don't know how severe it is. But with this estimated unconditional distribution to start with, and we simulate how this selection intensifies over age at recruitment, we see that the fraction of high preference for schooling types, they take over the population very quickly and very significantly. So this suggests that if we are using the RCT recruited eligible population to estimate the treatment effects, we are overweighting this particular type that's more likely to be eligible when we run at the recruitment, right? So that's going to cause the selection bias. Now let's go back to the very first goal of having this research. Is we have a structural model now, and we want to recover the policy ATE with full population and with longer durations. Right. So the way the counterfactual setup is we start with a population unconditional without selection from age 13, and we simulate the outcomes of this cohort subject to different durations of policy interventions. And we compare it to different cases, to no policy, 2-year policy, mimicking the RCT duration and the longer durations. So here is the outcome for the schooling. The dashed line is the baseline with no policy interventions, and the colored lines, they are the intervention, the schooling outcomes at the different ages over time with duration, with different duration, lengths of duration of policy intervention. And the key message here is that there's going to be very significant policy treatment effects. It's more clear if we take the difference between them, then it's going to be the policy treatment effects, and we contrast them to the RCT treatment effects, which is going to be these dashed lines. You can see the levels is almost like the 5 to 10 times difference because we corrected these two issues. So that's the key takeaway for this empirical application. So to conclude, our paper proposed a methodology of combining structural models with multi-arm RCTs to recover the actual policy ATEs, and by addressing this short-run and endogenous recruitment limitations that may exist with many RCT cases. And we found that a correction of this for the Malawi cash transfers programs tells us there's going to be 5 to 10 times larger policy treatment effects compared to the RCT estimates. And I just want one last sentence is that we exemplify this with the Malawi cash transfers program, but we think this is much more applicable to many other settings. Thank you.
We have no time for questions. You can talk about it now.
I don't like.
So next we have Dave Kang from
I need a mic. So in this paper, we study parents' aversion towards siblings inequality, and let's see what that means. So think about a household with k different number of siblings. Siblings have a ability endowment skills, Xi, and it might be different, meaning that some children are more effective in terms of generating future outcome, E, such as years of education. And that means there is a different opportunity cost investment for different kids. In such case, Becker and Tom study whether better endowments are reinforced or poorer endowments are compensated. Berman, Tom, and Pollack later extend Becker and Tom's by focusing on the inequality dimension, and they model this parental aversion to inequality among their kids. So depending on this phi parameter in the model, parents might be very averse towards siblings inequality. That would be the case that they view siblings education as the complement, and in such case, they would want to minimize the inequality as much as possible. On the other extreme, they might not be so much worried about the inequality among the siblings, and as a result of their investment behavior, they would end up increasing the inequality among the siblings. So yeah, this was interesting and important discussion in the literature, which has implications for household welfare and siblings welfare, intra-household inequality. But the parameter of interest has been difficult to identify because ideally what you need is some exogenous variation that affects some siblings of the household so you can identify how parents react, whether increase or decrease in inequality. But as you can imagine, such setting is very hard to find, so it's been difficult. And empirical evidence has been scarce regarding this topic. Okay, summarizing the motivation, our research question is, how do parents allocate resources within the household? Do they reinforce or compensate the difference among the siblings? In this paper, we leverage an intervention that assign conditional cash transfer at the individual child level, as opposed to family level. So by this particular feature, we encounter a situation that even though they are within the same household, some siblings are treated for the cash transfer, and some siblings are not treated, so they're untreated kids. And this CCT has been implemented in Colombia, Bogota. So this is the background that school attendance itself is a parental investment, because alternatively, you can let your kid work and contribute to the household income. And as CCT is targeted for low-income household, this is a significant opportunity cost for low-income household. So in our intervention changed this opportunity cost of schooling for some children in the household. And this is a setup that there's an exogenous variation that happens to some siblings that has nothing to do with the characteristic of the household, as it's random. And using that, now we can see how parents react to this random variation, whether they're gonna increase the inequality as a result of their investment behavior, or they want to minimize the inequality. So we identify parental aversion to inequality in offspring by leveraging this experimental variation. So for the first half of the paper, we just use data and OLS and identify the effect of conditional cash transfer effect. So CCTs have clear shown direct effect for school attendance and enrollment, but effects are not robust in the long-run outcome measured by college graduation. Importantly, we find negative spillovers on long-run outcome, which means that if you don't win the lottery, but your sibling wins the lottery, from the fact that your sibling is treated, the chance of graduating college for you decreased by 3.7%. So that's what we call negative spillover in this paper. Using the dynamic structural model of siblings education allocations, we rationalize this finding. In particular, we identify low aversion to inequality in offspring of the parents, which is consistent with the reinforcement behavior by the parents. At the same time, parental aversion has strong impact on intra-household inequalities. And using the estimator model, our conditional cash transfer also has some feature of indulgence recruitment. Correcting for that, here also we find a strong short-run effect outcome. But at the same time, unlike experiment, we also find a significant long-run outcome for college graduation in the policy as well. Later, using the estimator model again, we shut down parental aversion to understand the role of it. And we find shutting down parental aversion understates the effect of the cash transfer. So that's the outline of the paper. While I'm still receiving your attention, let me show you the key mechanism of the model, which is here household cares about the total outcomes of the siblings, which is measured by the number of kids who graduate college, more than years of education, 16. And they feel stress, they feel this utility from the inequality among the siblings measured by the variance of years of education. And how it connects to this negative spillover. So when rho 2 goes to negative infinity, they're very much afraid of the difference among the siblings. So the achievement difference collapses as rho 2 become negative infinity. And as rho 2 get closer to 0, they're not worried at all. And education gap increases. So negative spillover in general becomes stronger. And spillover effects from experimental variation tells us that among this whole domain of rho 2 from negative infinity to 0, in which value is consistent with the experiment, and we find something very close to 0. Okay, let me briefly talk about the CCTs. So this has been implemented in Bogota, Colombia in 2005. And the program was publicized in January, February 2005, and registration started on March 2005. And here, the prerequisite eligibility is the kids have to be in the secondary school, and parents have to be there. And since it's targeted for low-income household, they need to be categorized as a poor household. And also, recruitment is based on the attendance in 2005, so students had to be attending in 2005. Treatment is assigned individual level and randomly on April 2005, and transfer is given July, and 7 to 8 months later. The condition of this conditional cash transfer is the 80% attendance that you have to maintain throughout the secondary school period. And the short run measure, high attendance, more than 80%, low attendance, staying home work is collected 6 to 8 months later. And we managed to link our samples to the admin data set of Colombia, which tells us about whether these kids graduate college or not. So that's going to be our long run measure. And as this is admin data and short run measure is from survey, there's a little bit of difference in terms of sample size you can see later. So here in this first OLS part, we do 4 different regression, and some we are going to use for estimation, some we are going to use for validation. Starting with total effects, which what we call is just simple comparison between the lottery winner and lottery loser, regardless of which type of family you're from. And second one is indirect effect, which is more or less the focus of the paper. So the dummy here is whether you have the winning sibling. So let me dig into the identification strategy here a little bit. We focus on the 2 children household, as it is individual level assignment. There are 2 outcomes, treated control. So 2 to 2 is the 4 different type of household, which is treated, all treated group, treated control, treated, depending on the birth order, that there's going to be the some treated group, and control, which is going to be the pure control. In spillover effect, we basically want to compare between the losers. The only difference is whether you have a winning siblings. So estimation sample for indirect effects restrict to the lottery losers, and this is the way we identify the indirect effects in this regression. And next is the direct effect. So still we are going to use the sum treated household and pure control, but now we're going to use this red guy. And direct effect is comparing the winner from the sum treated household, and we discard the loser from the sum treated household, and we compare them with the control group. That's how we identify the direct effect, which is the winner dummy. And one last sample combination that I didn't mention is the 2 winner household. So here in this paper, the strategy is following. we estimate the structural model later using some treated household and the control group, and we estimate the parameter, and we use two winner household as the validation group, meaning that using the estimated parameter, we test whether we can replicate the behavior of the two winner household. Using this validation moments from the win-win lose-lose effects regression. The name is because there are two winner household relative to the control group. So this is the effect of coming from two winner household. So yeah, so that's the validation moments that we're going to use later. Results. Starting with the total effect, a simple comparison relative to the control group. If you win the lottery for high attendance, relative to the control mean of 62.3%, chance of doing high attendance increased by 12%. Chance of doing low attendance decreased by 8% relative to 27.7%. Chance of doing choosing work decreased by 3%. We don't find any long run positive effect or negative effect for long run outcome.
But if later, for example, they have switched,
Yes.
then still in the treatment group on the boundary.
So in our whole sample, we have 3-4 a household with 3-4 kids, and we restrict for two children household for two reasons. First is that later we want to be consistent with the structural model, and modeling 3 kids, 4 kids is going to be very difficult. And at the same time, yeah, so we use those what's that, 3-4 kids as a robustness check, and they can be found in the paper.
Most number of children.
Yes, most populated children are the 2 kids. Sorry, yeah, thank you. And for the direct effects, relative to total effects, we remove the 2 winner household and the loser from the sum treated household, and we compare winner of the sum treated household versus control group. And here we find the increase of high attendance 7.4%, short on attendance, but we don't find any statistically significant effect for other outcomes. For indirect effects, for long run outcome, relative to the control mean of 12.1% college graduation, if you are not treated, but your sibling is treated, the chance of graduating college decreased by 3.7%. So that's what we call again negative spillovers across the siblings. Right. So that's an important question. So for long run college graduation, the story I'm thinking is the swapping between so there is sibling who is more likely to success in graduating college and who are not. And conditional class transfer somehow can cause a swap between these 2 siblings. So now because of that, also promote more kids who actually was not supposed to go to college. But in that case, so that's the story that kind of rationalized the negative long run effect, even though it's not significant, and at the same time, negative indirect spillover.
Why do you have more observations for the long run?
Because it's from admin data. Yeah.
So all the control group are familiar household.
Yeah.
Both one is one. So you choose both siblings.
Yes, both siblings, yes. So for validation moments, for high attendance, we find a strong increase in high attendance, 15%. For low attendance, also, we find a strong decrease in low attendance outcome, 10% decrease, and for work, 3% decrease. We still find no effect for a long run college graduation outcome. Okay, so for structural model, what we want to do is we model the behavior of low-income household with 2 children. And household differs by the age of the first kid, which is the cohort, and the spacing, age difference between the siblings, and their parents' income, YP, and children income, YC1, YC2, and the ability of the siblings, either high or low. So if there are 2 different siblings, there can be 4 different types of household in terms of the ability of the siblings. And unobserved preference shocks for each choice. So household make decision for each kid, 4 different decision of high, low, home, work decisions. So 4 to the 2 is 16 different decision every period. And in 2005, conditional cash transfer comes as a surprise. Then household become different if they are eligible in terms of CCT assignment and Z and the transfer amount tau. In this model, ability enters into the probability of progression to the next grade. Skipping the flow utility, and at the final period, when the second kids becomes age 25, they collect this terminal value from row 1 time number of kids who graduate college plus row 2 times the inequality among the siblings, which is measured by the variance of the education. So they make 16 different decisions subject to the budget constraint. And if let your kid work, budget is going to be increased. And probability of progressing depends on the attendance choice and your ability of the siblings. And there's an income generating equation for parents and the kid. So they make this choice business as usual before 2005. And as they differ in terms of the first kid age and the spacing, they arrive differently to 2005. So some have kids who are both kids are in the secondary school, and some only one, and some both of kids are working, and some both of kids are doing high attendance and so on. So in 2005, RCT comes as a surprise, and if you're eligible, meaning that the 2 kids are both in the secondary school, and both are either doing high or low attendance, just attending school, you get a shock to the budget constraint, and if you're treated, Z is not controlled. And as long as you maintain high attendance through the period for that child, you're going to get the transfer tau. So that's how we model this RCT.
So you will see that the total household resources is fixed, and there is only a change in the resources allocation amount of children.
Right. So actually, transfer entered into the total household income. So yeah.
Get the transfer, so the work less. That also
Yeah.
Check out the overall resources.
Right. So yeah, we are not modeling the work decision of the parents, but we assume parents work throughout the period, and that's what the data tells us too. So, right. No. Yeah. Okay, so how we estimate the model? We use method of similar moments, and the moments we match first is the school attendance, staying home, work decision by age for observation of population outside the experiment. And they arrive differently, as I said, to 2005. And if you're in the experiment, so we match the behavior of the control group in the experiment. And if we successfully capture these 2 differences, we can capture this indulgence recruitment that's discussed in the previous presentation. We match the short run and long run direct, indirect effect regression moments. And other moments relate to re-entry behavior and a graduation penalty if you do low attendance, and different graduation rate by birth order as well. Importantly, we are not using all treated household, 2-winner household for estimation. We keep as a holdout sample for validation. So starting with the direct effect and the control mean, we capture the data column and the model column. We capture the control mean pretty well for high attendance, low attendance work, and college graduation. For direct effect, we capture the 7.4% increase in high attendance, and model is 7.6%. And other coefficients are also within the confidence interval. For spillover effects, importantly, we capture this negative spillover from your siblings' 3.7% decrease in your graduation probability. So we exactly capture that number using our structural model. Behavior within experiments. So control group behavior in the experiment. So this is age different decisions in 2006. So if students get older, there's a slight decrease in high attendance and increase in low attendance. And these people don't really work who are in the experiment. And the working starts in 16, 17, 18. Using the model, we capture all this within experiment behavior. Now let's look at the people who are outside experiment observation population. So there is a steeper decline in terms of attendance and steeper increase in work and the low attendance as well. And we kept using our model, we capture the behavior of people outside experiment reasonably well. So we view that we capture this endogenous recruitment and the difference between the observation population and the people who are in the experiment. We paid particular attention to this ρ2 parameter in this paper. And if you think about the negative spillovers, it's really the sample mean difference between the treated group and the control group. And here the treated group is you're not treated, but your sibling is treated. And the control group is there. And the treated group's gradation is lower by some percent relative to the control group. We both capture the level of this different two group pretty well. And with some adjustments coming from other covariates, we also capture the indirect effect pretty well. And the value of ρ2 that is consistent with these moments is negative 0.085 among this whole domain of ρ2 from negative infinity to 0. And this is very close to 0. Okay, I'm gonna skip some detailed parameter estimates. And for validation group, we capture the strong increase in high attendance. It's not exactly 15%, but it's fairly close and within the constant interval. And for low attendance and work, we are doing a better job there. And also within the constant interval, college graduation is not significant, but still the number is within the constant interval. So that's how, and we view our model is validated by capturing this validation. Okay, some time for counterfactual. So the purpose of doing counterfactual is first understanding the role of ρ2 in this conditional cash transfer experiment and the behavior of the household and the intra-household inequality. So we do two policy. First policy is policy where both children are treated from the beginning to the end of the secondary school. So for both for both policy, unlike experiment, this is not based on the calendar year. We treat them from the time they start attending the secondary school. So that's how we correct for this endogenous recruitment in the policy experiment, policy simulation. In the second policy, here parents have to designate which kid is going to be treated. And for these two different policy, we simulate for different amount of stipend up to twice of the baseline policy, which is done in actual experiment. And we compare with ρ2, with means that we use estimated value of ρ2. Without ρ2 means that we basically shut down the ρ2 channel, fixing it to 0.
Do you have any heterogeneity like the other receiving?
We do in the reduced form part, and we have like very small difference by gender. So we are not modeling that as a part of state variable in the dynamic discrete model. But that's a good question. And yeah, as I said, we correct for endogenous recruitment and we can recover true policy effects. as the previous paper, previous presentation. So here, the outcome we are looking is the first column is SR10 sure-run attendance. Second column is the college graduation. Third column is intra-household inequality. Sorry, the first row is estimated aversion, where I use a estimated number of row 2, and no aversion is the row 2 is 0. And we do this for no treatment and different policies. So the policy effect of both children being treated is 7%, and the comparable setup in the experiment is the win-win lose-lose regression, and there it was 15%. So the effects are quite different for short-run outcome and long-run outcome as well. If you compare the policy 1 to no treatment, there is an increase in 1% of college graduation, as opposed to 0.2% increase in the experiment, and this was not even significant in the experiment. Reason is that we compare the ability types of the siblings within the experiment and outside the experiment population. We find that experiment has a fewer first high and second low household, and low household are kind of overrepresented in the experiment, and experiment more likely to recruit students who have high ability younger sibling. So that kind of makes somehow makes the short-run attendance larger and long-run attendance smaller. And the spacing, let me skip that. For now, I'm gonna shut down aversion and see how that makes difference in terms of the total outcome and the intra-house inequality. So when I shut down row 2, that increases intra-house inequality from 2.80 to 5.36, measured by the education gap between the siblings, which is a very big difference. But at the same time, interestingly, if I shut down aversion, the total outcome of sibling average college graduation increased by 4%. So we can see household is doing this efficiency equity trade-off from the channel of row 2 by comparing the case of estimated aversion versus no aversion. Now to see what's the implication of this to the actual policy, we explore different amount of stipends starting from 0 with estimated row 2 in the first panel and shut down row 2, 0 in the second panel. And what we find is that in the second column, this is college graduation outcome, effect is basically flat when there is no aversion. This is because households are already doing the specialization among their siblings, so there is a very little room for policy improvement. But in actual case, in the estimated aversion, there is quite a strong policy gradient relative to the no treatment. And this is same for short-run attendance outcome as well. So we find shutting down row 2 would understate the impact of the policy on both outcomes. And I'll stop here. Thank you.
Question. Yeah. If you want time for questions, try to finish 5 minutes before your turn.
Last one for lunch is 5 around the
Okay. So I'll jump right into it. I'm talking about experimental design for policy choice. So what exactly do I mean by that? So of course, experiments that we've seen throughout this conference are a increasingly widely used and very valuable tool for data-driven policymaking. And so I've just listed here some kind of high-profile examples of large policy-oriented experiments from the last 20, 30 years here. And so when I talk about data-driven policymaking, I have something like this sort of timeline in mind, where we have some type of objective that our policy is aimed at targeting somehow. We go out, we collect some evidence. There's, of course, many ways we can collect evidence, but I'll be talking exclusively about experiments today. We use that evidence to choose some kind of policy, and then we'll roll it out to the broader population. And so the question I want to examine in this paper is what exactly makes an experiment optimal for choosing a policy. The reason I think this is an interesting question to ask is that a lot of times experiments are designed to maximize the power of certain hypothesis tests or the precision of certain parameter estimates. For example, the average treatment effect of some type of intervention. However, detecting the presence of these types of effects is going to be neither necessary nor sufficient for choosing a good policy. For example, estimating an average treatment effect very well may not tell us how to allocate the treatment to a heterogeneous population when we have some constraints on the total amount of the population. And so rather than just asking how do we estimate an average treatment effect very well, we'd like our experiments to help us answer questions like, should this tax or subsidy be higher or lower, and how do we want it to vary across the population? And so this means I want to view the experimental design and the policy choice questions jointly together as a dynamic decision problem. That is, we want to take this policy objective into account explicitly when we're designing our experiment. So I have this motivating example of Progresso, which I'll refer to throughout the talk, and we'll talk a little bit about it in a little bit more detail at the end, which was this large-scale conditional cash transfer program in Mexico, which offered money to families conditional on their children attending school. And so we're going to suppose that we're, some policymakers, and our objective is to increase the graduation rate within school. Well, also, we might care about keeping the gender gap in graduation rates low as well. And so the type of experiments we can run, and the experiment which was actually run for this progressive program, is to randomly offer some money to different types of children, where this amount of money can vary by the grade the child is currently enrolled in, as well as the gender of the child. Once we run our experiment, then we can choose some policy which allocates money to different types of children. But importantly, this policy that we roll out does not have to be the same type of thing we tested out in the experiment, right? The experiment is to teach us something about the responsiveness of these households, and we'll use that to design some potentially different policies. And so to model the effects of these counterfactual policies, which we're considering but may not have explicitly tested in our experiment, I'll be using a dynamic school choice model, which has previously been used in literature to study the progressive experiment. And so the question I want to ask is, could a different experiment than the one that was actually run in Mexico 20, 30 years ago, could that reveal more about the optimal policy that we're after? To give you an idea of kind of the interplay between these questions about how to design the experiment and how to choose the policy, I want to just look at kind of some of the choices we have to make in each of these two phases. And so we're choosing a policy, we need to basically decide how large should the subsidy be, how should it vary by observable characteristics, and then what type of constraints are we going to face on this policy, except in terms, of course, what's even feasible to implement. Yeah.
Usually experiments are at small scale.
Yeah.
Policies at large scale.
Yeah.
But are you gonna say something about the equilibrium effects, large scale policies?
So yes and no. For example, when I get to the empirical application, I'm going to be following this Atanazi background Santiago type of approach. In that paper, they actually model the equilibrium effects of this program on wages. In my sort of simplified example, I actually dropped that part of their model. But the method I'm presenting is general enough that whatever model you had, if you could think about modeling those type of equilibrium effects, you could take those into account explicitly. And so in that way, it's kind of like it's as rich as your model is going to be. And the method I'm proposing here isn't tied to one particular model, but it can be applied more broadly to whatever model you have in mind. Okay, so when we're designing this experiment, we want to kind of gather information that's going to be useful for making these types of policy decisions. And so the types of questions we need to answer is, for a given experimental budget, would we rather have a large subsidy that we give to a small experimental group, or would we rather have a smaller subsidy that we can give to a larger treatment group. Also, we want to focus our experiment on particular subgroups that we think might be especially policy relevant. So a key quantity that's going to emerge, which is really going to drive kind of the design of the experiment, is this marginal effect of adjusting our policy. So in this progressive example, this is, we want our experiment to help us answer the question of should an extra pay. So if we had a little bit more budget, would we rather give that extra money to boys or girls in primary or secondary school? And answering this question is actually sufficient to characterize the optimal policy, at least in kind of a local sense that I'll make precise a little bit later in the talk. And the optimal experiment is going to basically focus on estimating these parameters very well, and I'll show you precisely how that works. So taking a step back from the progressive example for a moment, I just want to emphasize that this method I'm proposing is a general method for designing experiments around policy choice questions. And when I say it's designed around policy choice questions, I mean it will be tailored to the particular objective and constraints that the policymaker faces. I'll show you that the experimental design I'm proposing is going to be asymptotically optimal, meaning the kind of the policy you get out of this two-stage procedure is going to have the highest expected welfare out of all possible experiments. So the design of the experiment, I already talked a little bit how it will be informed by the objective and the constraints which are faced by the policymaker, but of course it will also be informed by the particular model you have, because the model we're using is going to basically tell us how to link this experimental variation to the kind of structural parameter model, and therefore the different counterfactual effects of various policies we could be interested in implementing. I'll have two theoretical results which make this experimental design policy choice problem tractable. I'll spend, I guess, relatively less time on them today just because of time constraints, but if you're interested in the theory, there's more of it in the paper. The first result will be to kind of basically characterize the information environment, the information that our policymaker is working with. We can characterize it by a Gaussian limit experiment. That's the term that they've used. And then this policy choice problem, we can show that kind of very general, complicated, nonlinear policy choice problems can also be approximated by a quadratic program. And together, these two results will imply that marginal effect I referred to on the last slide, how much money, if I had an extra peso, whether I'd ever give it to boys or girls in primary or secondary school, these results will imply that effect is kind of the sufficient statistic for this policy choice. So here's kind of the outline of what I want to talk about. Just to give you an idea of how this two-period dynamic experimental design policy choice problem works, I'm going to set things up in a very simple setting where we have Gaussian data and our objective is quadratic. Of course, when we're thinking about the progressive example, we don't have Gaussian data, we have a large and complicated data set, and we don't necessarily have a nice quadratic objective. So then I'll kind of show you kind of more generally what these problems look like. And we'll see that in general, solving these types of experimental design, dynamic experimental design problems, they're quite intractable. We're going to go around this by basically showing you that this simple Gaussian setup and then the more complicated general setup, they're asymptotically equivalent. And so that means that this kind of easy problem I'm about to show you can use that as an approximation to these more complicated problems that that. And then finally, I want to spend a little bit more time going back to the progressive example and showing you exactly what this method implies about how we should think about gathering data for choosing policies. So let's set up this sort of simple example first. The timing is as follows, in what I'll call period 0, kind of happening before we're making any decisions. We have some prior. I'll talk a little bit later about where that prior might come from. We're going to choose how to design the main way of the experiment. Delta will be our decision for the design of the experiment. We'll observe some data. On the basis of that data, we'll choose a policy, which I'll call C. And then at the end of this, we'll receive some welfare based on the policy we've chosen. And so the set of feasible designs is going to live in this space delta. Once we choose our design, we're going to observe a Gaussian signal, H hat, with variance given by J of delta inverse. I'm going to assume that we know the function J of delta. So if I change delta, I get a different variance for my signal. This is multivariate, by the way. H is multivariate. We have some linear equality and inequality constraints on the set of feasible parameters, and we have a nice simple quadratic welfare. So I'm going to set up this sort of dynamic program that the policymaker is trying to solve. In the second period, in the future, when we're trying to choose this policy, we want to maximize our expected welfare from this policy, subject to some constraints, given kind of our posterior action with observe this data. H is the unknown parameter we're trying to learn about. This will define the value function of basically different data observations. In period one, then, we want to choose our experiment design in a way that will maximize our expected value, subject to whatever constraints we have, given our prior. Okay. And these two periods are linked through the law of motion, which is basically the experimental design process. We choose our delta, we see our data, we form posterior. Okay. So that's the general structure that we're talking about. Just sort of plugging in things, function formed here. You know, we're maximizing our expected value. We're maximizing this nice quadratic function where I'm just taking gamma to be this linear coefficient on our policy C. This will define the value function, which we call V, and the state here is going to be our posterior on this sort of coefficient on C. And then in period one, we want to maximize our expected value, where again the law of motion as before is just given by the. Okay, so I was just adding a little bit more notation to the previous slide, but if we have this sort of simple Gaussian quadratic setup, solving for the optimal experimental design would actually be quite easy. It's kind of just a standard value function approximation procedure. You can sample a bunch of points from the state space, using whatever method you like. Compute the value for all these sample points, which is a quadratic program. Interpolate using whatever regression model you want, and then you can choose our delta to maximize our result. And so in this very simple setting, solving this type of two-period decision problem is pretty straightforward. But it appears at least that it might be too simple to reflect actual experiments, right? Because in this progressive example, we have this nonlinear dynamic structure model about how households are choosing to send their children to school. We have a potentially complicated welfare function involving this long-term behavior of graduation rates. So let's talk a little bit more about kind of a realistic set. So in general, we're going to be assigning some treatment Z for a population. X are some covariates. So we can assign this moneyed households conditional in their observed covariates. Treatment can be a lot of things. It can be binary, it can be continuous, it can be multidimensional. In the progressive case, we're thinking about assigning both the amount of money I'm offering household today, but also the future subsidy, because households are forward-looking, and if I offer them a bunch of money 3 years from now, it's going to affect it. We're going to have some model. Again, it's going to be a lot of things. I'm using a dynamic model. We can think about modeling equilibrium effects. But for this paper, I'm going to be focusing on parametric models. And in this progressive example, I have this dynamic school choice model. And we'll have some set of feasible policies. So the types of policies that we can consider here, again, is pretty rich, right? Because we have a structural model with which to evaluate counterfactual. So we can think about policies like new taxes or subsidies or changing prices. The types of policies that we might implement might not be the same exact thing we're testing out in the experiment. In Progressa, we are going to be designing a policy which allocates money to the population of children on the basis of their observable characteristics. And we'll have a budget constraint on the total amount of money we can spend, and we also want to restrict subsidies to be non-negative. We don't want to be taxing these kids. And then finally, we have some welfare, which we care about. And again, just like the model can be rich, the types of welfare we can consider can be similarly rich. Progressa, I have this long-run completion rate as a welfare. which again gets to these issues of distinguishing between the experimental effects and the policy effects that we're interested in. So here I'm just going to kind of set up the same exact problem I had before, just kind of with a more general notation. So I don't want to spend too much time on this, but again, when we're choosing a policy, we're going to be choosing our policy pi, that's the amount of money we're offering in progressive setting, to maximize our expected welfare, subject to our constraints, given all the data that we observed in the experiment. Again, we can think about trying to choose the experimental design which maximize the value of our policy choice. And again, we link these two periods through basically the experiment. It's the data generating process for our data. And so basically we choose our design delta. That'll determine how the treatment Z is assigned to the population. After we've assigned the treatment Z to the population, then we observe Y, which is the outcome, whether or not a child goes to school in this period. And then that data set becomes an input for a policy. Okay, and so while I think the overall structure, of course, was very similar, this problem in the more general setting is much more difficult. And the challenge, which is kind of widely recognized in the adaptive experimental design literature, is that the state space is just extremely high dimensional. Basically, to solve by brute force, we have to compute the value of our policy choice problem for every possible data set we could collect. It's something we very clearly don't want to do, even in simple settings with binary treatment, only a binary outcome, three-dimensional treatment. We're already very, very quickly in thousands of dimensions. And so this is just to illustrate kind of like the difficulty of actually solving this two-period dynamic decision problem of experimental design in real example versus kind of the quadratic example. And so I'll show that this problem, while very challenging to find examples, is actually going to be approximately equal to this quadratic Gaussian problem I showed you a little bit. It's tractable because, as we just saw, it has this much simpler structure, which we can actually feasibly solve. It's interpretable because it's going to rely on basically the marginal effects of this policy. That's that coefficient on our policy is going to have a nice intuitive interpretation. And finally, part of my results imply that this experimental design is asymptotically optimal. This means that when we make these approximations, we're not actually losing any valuable information in the limit. Okay. So just in the interest of time, I'm going to go over some of the theory a little bit quickly, but of course, it's in the paper and we can talk more if you're interested in it. But at a high level, there's kind of two approximations we're going to make, and they might be sort of familiar to you from kind of classical efficiency results. One is to say that we have this whole data set, but it's going to be summarized by an efficient estimate, which is going to be our maximum likelihood estimator. We have to do a little bit more work to make sure this holds uniformly across the types of designs we're considering. But that kind of allows us to just pay attention to a Gaussian estimate rather than the full data set. Now, the second approximation will say that our value of the policy choice, which was V in the kind of more complicated problem, is approximated by this quadratic program, which I showed you earlier. And so this feels a little bit like kind of classical results on extreme estimation, where we have some loss function that's approximately quadratic. It's complicated a little bit by the presence of constraints, but essentially we can show that this quadratic program gives the directional derivative of the value function, and that justifies using this quadratic program as an approximation to the actual policy choice problem we're interested in. So we're going to suppose that we have some prior on our parameter theta. These are the parameter of structure of model. We're going to assume this is sort of asymptotically informative. Just in the sense that this H, which I showed you in the quadratic problem, corresponds to kind of the rescaled version of our parameter from the actual finding sample problem. And so H hat, this Gaussian signal, is just going to be, again, asymptotically equivalent to our maximum likelihood estimator. So that's sort of the mapping between the Gaussian problem and the finite sample problem. Likewise, we can kind of look at the optimal policy problem, which is to maximize our sum welfare function subject to some constraints, and construct basically a quadratic approximation to our welfare. So capital W, that quadratic welfare, is just computed by taking a quadratic approximation to the welfare, essentially. And likewise, we can replace our nonlinear constraints with linear constraints. Again, kind of just doing a tailored approximation to our welfare and constraints. Just in the interest of time, I'm going to skip this a little bit and kind of show you the high level results. There's two parts to it. The first to say that kind of whatever design delta or policy pi we chose in the original experiment, we can choose in a very complicated way with whatever algorithm you want. Asymptotically, it can't do any better than the optimal thing, that Gaussian problem. So this tells you that the Gaussian problem essentially serves as a bound to the best you can do in that finite sample problem. Part two is to say that if we were to take that quadratic problem I showed you, solve its empirical analog, we can actually hit that lower bound, right? And so when delta hat is the design we get from the quadratic problem, again, pi hat is the design we get from solving that quadratic program, then we're actually going to hit this lower bound. Okay, so this tells you that solving that kind of Gaussian quadratic problem is asymptotically optimal. It's doing the best we can possibly do, given the data that we have. And so that's what I mean when I say we don't really lose anything by solving the simpler quadratic problems. So I want to interpret this a little bit because there is some intuition in kind of the mapping between these problems. And in that quadratic problem I showed you, this policy choice only depended on basically their posterior on this coefficient on our policy. And what this is exactly our marginal effect of adjusting our policy in any direction. So this gamma is really just telling us if I gave a little bit more money to boys or girls in primary or secondary school, how much would I increase my welfare graduation rates by? And if we can get a good estimate of this marginal effect, then we can solve this sort of quadratic problem I showed you, which tells us exactly what the optimal policy is. And the intuition here is that, even though we have this rich model, which is kind of defining our counterfactuals and telling us what would happen if we have the graduation rates, if we change our policy, at the end of the day, when we're trying to maximize welfare, we're going to kind of take as a sufficient statistic from that model just the welfare effects, right? So really, it's just the welfare effects of our policy, which we care about for designing policy, and so good estimates of kind of policy adjustments are sufficient to choose the policy. So just really quickly, I want to spend just a couple of minutes talking about the progressive example. In this program, they assigned about 60% of people to treatment. They observed that this had positive effects on enrollment, and then they rolled it up to the broader population. We're going to say, suppose that we could design a different experiment, and we want to target this in a way that helps us learn about the optimal cash transfer policy. How much better could we do, basically? I'm not going to cover the model. I do want to leave a little bit of time for questions, and I don't want to keep people for lunch. But it's kind of a standard dynamic discrete choice model that households are solving, and we can estimate by maximum likelihood. Our goal is to maximize the fraction of people that are children that are graduating. So that's that first term, and then we also might care about gender inequality too. That's that second term, our welfare. In our policy, we're going to be choosing the amount of money that we give to children in every grade. We can change the amount of money by the gender of the child. Likewise, in the experimental design, we're choosing how much money we're giving to children in different grades, different genders. We're also choosing the treatment probability. So I can decide that I'm going to take girls in secondary school and I'm going to treat them all, because I really want to understand their responsiveness to this gas transfer program. So it turns out that the optimal experimental design in this setting, for the purpose of learning about how do we go about maximizing school completion rates, is going to focus exclusively on children in secondary school. And we're going to be treating a relatively high fraction of children in secondary school, 77% of boys, 67% of girls. We're not going to run this experiment at all on children in primary school. And basically the reason for that is based on pilot data. It appears that just children in primary school are not very responsive to the subsidy. For the purpose of designing exactly what this optimal subsidy will be, we really want to understand, are boys or girls in secondary school more responsive to this policy? And so when we're thinking about how to design this experiment in a way that tells us about the optimal policy, we're just going to focus our experiment on that sort of policy relevant population of children in secondary school, and really learn that marginal effect, that relative responsiveness of boys versus girls. We want to learn that very precisely. That will tell us exactly what the policy should be. The last thing I want to leave you with is just sort of these plots of basically the expected welfare gain that comes from focusing our experiment on the policy relevant question. So the green up there at the top is the expected welfare you would get if you if I already knew what the parameter was, I didn't have to experiment at all. The purple line is the expected welfare that you get from running the kind of optimized experiment, and then on the basis of that data, choosing a policy. The orange line is what you would get if you ran the original progressive experiment, and then on the basis of that data, chose an optimal policy. So I want to emphasize that the gains here are coming entirely through the choice of the experimental design. In both cases, we're optimizing policy. For the purple line, we're choosing a policy on the basis of basically more informative data that was gathered explicitly to tell us what the optimal policy is. And I think the gains are significant. So just to conclude really briefly, I think in this paper, we're kind of showing that your policy objective is really important for designing the experiment. And depending on what you're trying to learn from this experiment and what you want to use the data for, you should maybe think a little bit about what's the most effective way to go about gathering my data, where do you want to focus my experiment. But that's everything for me. So let me know if you have more questions or you want to talk a little bit.
1 minute. I have one question. Is I was thinking of a very interesting maybe topics in China. When how to say for example, the central governments want to implement some policy in some region or some broad way or national level, they will always have some experiments in one place. And at that time, I think a lot of local people will, especially local government officials, will try their best to make the local experiment effect better than ordinary expected, and always have a good effect. Then central government say, okay, that area and have a good experimental result outcome. Then let's spread in the whole nation. But in fact, if really spread in the whole nation, maybe the effect is not as good as we expected. And how to solve that kind of problem. And that's the I think the topic I know a lot of people or a lot of countries are quite interested. That's my question.
Yeah, no, that's a really good question. Thanks for that. And it is an important one, right? When people try to scale these experiments, few policies often get used to those types of smaller effects. I'll say a little bit what I said earlier about equilibrium effects. So I think there's kind of some similarities there, which is one reason that you might have smaller effects when you scale things is maybe some kind of equilibrium effect, where I mean, in this progressive example, you give one kid money to go to school, it goes to school. You give everybody money to go to school. You also go to school, that's going to affect wages in the local labor market, and that sort of undercuts the effectiveness of this. And so that's not something I can really explicitly address in this paper, except by saying that insofar as your experiment can tell you something about these types of scaling effects, again, that should be sort of built into your model and your welfare function, rather than just trying to kind of like blindly say, oh, an average treatment effect is what we're after, let's just find this. We do want to think about all those things, but it's kind of more of a question I think about your model, for example, than maybe with your plan.
Because when we do some, how to say, just do the parallel trend test, you will see in the earlier stage is the, experiment times.
Yeah.
And the effect is quite good.
Yeah.
And but really the policy implemented in that area, but not good as before.
Yeah.
So that's that kind of designs, effect. I feel there's a Wang Shao that I once mentioned that kind of, effect in China.
Mhm.
And I thought maybe, we can also consider that kind of case into the policy design.
Yeah, I think we're a little out of time, but we should talk more. It's very.
All right, so this comes the sessions in the morning, and lunch will be provided outside of the, portion. Please do enjoy. And then we will resume. 40 minutes. Break, so 5 years, so.